Hi everyone, in this lecture I want to continue the band pass and band reject filter. So my focus is going to be on band reject filter this time. Okay, so we're going to talk about band reject filters in this lecture. A band reject filter has a frequency response plot which lets input frequency component to go through the circuit if their frequency is low or high, and if they are within a range in the middle frequency, then it will stop them. So it has a frequency response plot like this. So this is an ideal band reject filter, which is rejecting the frequencies in the middle band, and it will pass all the frequencies that are outside of this middle band, which has a range from omega C1 to omega C2. So this is my lower cutoff frequency and this one is my higher cutoff frequency. Now let's see how we can make a very simple band reject filter. It's not going to be an ideal band reject filter, but let's see how the transfer function of an RLC circuit for a band reject filter looks like. So I'm going to start here with the standard form for band reject filter transfer function. So if we have a transfer function which has a second order polynomial in denominator, then we can say that it's probably referring to a band reject or a band pass filter. So having a second order polynomial in denominator will show us that we are looking at a band pass or band reject filter. So s squared plus beta s plus omega naught squared in denominator. And then, so this is something in common between both band pass and band reject, but the difference is in numerator. So if in your numerator, according to our previous lecture, if we have a coefficient of s, then that's a band pass filter. But if you have s squared plus a constant, then that refers to band reject filter. So if you have s squared plus omega naught squared in numerator, so s squared plus a constant, then that refers to a band reject filter. And remember that this is a very simple transfer function for a band reject filter, and the response characteristic is something like this. Which is similar to an ideal band reject filter, but it's not an ideal situation. So we can say this is something that we can estimate by a band reject filter because it has similar characteristic, but it's not going to be a sharp transition from pass band to reject band and vice versa. So this is going to be the transfer function that we can say it refers to a band reject filter. Now let's take a look at this transfer function and see why we can make such an assumption. So I want to look at low frequencies and high frequencies. So in low frequency, I can say s squared and s are close to 0 because my frequency is approaching to 0. So this term, and this term will be eliminated. And what I have left is omega naught squared over omega naught squared, which is equal to 1. So h at j omega, in which omega is a very small frequency, approaches to 1. Now, for high frequencies, if I'm assuming I'm looking at higher frequency, then this time I have to look at the highest degree in numerator and denominator. So highest degree in numerator is s squared, and highest degree in denominator again is s squared. And if I divide them, I have a constant of 1. So again, h at j omega approaches to 1. So you can see that for very low and very high frequency, I have a value close to 1, and then in the middle frequency it will drop to somewhere close to 0. And the frequency that the magnitude of h of j omega is equal to 0, exactly equal to 0, is called my center frequency. And you can see that if you plug s as j omega naught, j omega naught, then the numerator will be equal to 0 because s squared will be j omega naught squared, which is equal to minus omega naught squared, and then it will cancel out omega naught squared in the numerator. So omega naught is our center frequency in which the magnitude of h at j omega naught is equal to 0. And similar to what we discussed for band pass filter, we do have cutoff frequency. So let me erase this here. So here I have omega C1 and here I have omega C2. So this is basically the frequency that shows the cutoff frequency for me. And in cutoff frequency, the magnitude of h at j omega is equal to 1 over radical 2. So if I want to directly find omega c and omega c1 and omega c2 from the transfer function, I can let the magnitude to be equal to 1 over radical 2, and I can solve for omega c1 and omega c2. But we do have other approaches by using equation that describe omega c1 and omega c2 based on omega naught and beta. So I'm going to write the equation one more time here. The equations are basically similar to what we have for band pass filter. These are the equations. So we know that beta is equal to omega c2 minus omega c1, and omega naught is equal to radical omega c1 multiplied by omega c2. And if you're looking for quality factor, the quality factor is equal to omega naught over beta, which is our bandwidth. So these are 3 equations, and if you know 2 parameters out of 5, then you should be able to find the rest of them. And these are our 5 parameters that you need to find for any band pass or band reject filters. You need to know about omega c1, omega c2, beta, omega naught, and q. So if you know 2 out of 5, you should be good and you can find the rest of them. Okay, now I want to show you an example that show a behavior similar to what we are interested in as a band reject filter. The circuit that I'm going to use is exactly similar to what I showed you for band pass filter, but with the only difference that instead of using the voltage of resistor as my output, I'm going to use the voltage of inductor plus capacitor as my output. So let me draw the circuit here quickly. This is the exact circuit that I used for band pass filter. So what I'm using is a series RLC circuit. For band pass filter, I showed you that in order to see a behavior similar to what we are looking for band pass filter, we have to look at the voltage of resistor. So we focused on the voltage of resistor. But here, instead of resistor, I'm going to focus on the voltage across the inductor plus capacitor. So together, I'm going to consider them as one merged impedance, and I'll consider my output voltage to be the voltage across this merged impedance. Now let's see how the behavior of this circuit will be if my output is defined as the voltage across inductor and capacitor together at the same time. Now let's look at the behavior of this circuit in low and high frequency. In lower frequency, I know that the impedance of inductor is very small, and I'm going to have an impedance approaching to infinity for 1 over Cs because S is approaching to 0. And then the resistor has a constant value for its impedance. And then in high frequency, this time the impedance of my inductor is huge and the capacitor has a very small impedance. Same for resistor if I want to consider that with compare that with my inductor impedance. Okay, so now as you can see, it shows you that if you're focusing on the voltage across these two elements, inductor and capacitor, as your output voltage, then together they have the biggest portion of the input voltage. So if you have a low or high frequency, then one of these two will be a huge impedance, which basically, if you think about the voltage divider, then the voltage divider happens across different impedances according to their impedance. So if you have higher impedance, you will get more voltage. Now, if one of your impedances is infinity, all the voltage will drop across that element. So considering these two as one impedance, together they have an infinity impedance. So in both scenarios, VO will be very close to input voltage, which is VI, which basically means that VO over VI is almost equal to 1. So the magnitude of H at J omega, if omega is approaching to 0 or if omega is approaching to infinity, in both scenarios the magnitude is very close to 1. And that's what we know for band reject frequency. But in the middle frequency, so if I think about middle frequency, what will happen is that they have an impedance which is in the same range. So LS has an impedance very close to the value of 1 over Cs with opposite signs, so they basically cancel out the effect of each other. And this time, because these two together are very negligible, the input voltage will mostly drop across the resistor. So if I'm focusing on the voltage of inductor and capacitor together, the voltage drop will be very small, so VO would be very close to 0. So it means that the magnitude of H at J omega will be close to 0. So that's what I'm basically looking for a band reject filter, something like this. So 1 for low and high frequency and something around 0 for middle range. Okay, now that we know that this particular circuit behaves like a band reject filter, let's look at its transfer function. So if I'm looking for the voltage across inductor and capacitor, I have to use a voltage divider in which in numerator I'm going to have the impedance of these two elements together. So my H of S, which is basically describing VO over VI, will be LS plus 1 over CS over LS plus 1 over CS plus R. Let's multiply everything by 1s. So this one will be s squared. I'm gonna remove s here. I'm gonna remove s here. I'm gonna make this one ls squared and r multiplied by s. So I'm multiplying everything by s in order to get rid of s in the second fraction, in the numerator and denominator. And then I'm gonna multiply everything by 1 over L, which is the coefficient of s squared, to make it look like my standard form. So if I rewrite my h of s, after multiplying both numerator and denominator by 1 over L, I'm gonna have s squared plus 1 over LC over s squared plus r over L multiplied by s plus 1 over LC. Now, according to the standard form for band reject filters, I can say that this 1 over LC, which is my constant when my polynomial in denominator is in a standard form and the coefficient of s squared is equal to 1, can be considered as omega naught squared. And the coefficient of s will be my beta. And then remember that I can verify and I can confirm here that this, if I look at the voltage of inductor and capacitor together, I'm gonna have a band reject filter because of what I have in numerator. So it verifies that I'm looking at a band reject filter because I have s squared plus a constant in numerator. And then having omega naught and beta, I should be able to find all other parameters for this circuit.